So big data is a term that's come up in the last 4 or 5 years, and it is meant to signify a whole bunch of business models that are based on collecting large volumes of data and finding relationships in the data. I think big data is a bad term. We should actually be using the word data science. Data science is a broader term that actually captures the algorithms, the data, the business objectives, the visualizations, the presentation of the data and its results. So it's really a bunch of things that are built around large quantities of data, but many of these things are also theoretical. So for example, Google has an algorithm that tries to optimize the bidding process for the auctions of AdWords on their website, and that is a technical algorithm based on game theory that's implemented on a reasonable amount of big data as well. So big data doesn't tell the whole story. The terminology data science is better because it includes the theory and the data and the algorithms that bring these two things together. So machine learning, as it was originally defined, was the idea that machines would be autonomously learning for themselves. Most of the time, when we use a machine or a computer or a piece of software, all the rules have been already introduced into that package or the software by humans. And so those portions of the algorithms were not originally envisaged by machine learning. Machine learning was that the algorithms in software would actually learn about the data and then actually make decisions and build future algorithms to exploit the data as well. We are getting there. So the right extreme of machine learning is AI, which has now become very hot. And we've just seen this last week that the DeepMind computer that Google has actually beat the world Go champion, which is supposedly a very hard problem to solve. It won 4 out of the 5 games. When you get to the AI side of machine learning spectrum, there the structure of the problem and the future manifestations of the solution or the software solution or the algorithm actually gets determined by the machine itself. And so in some sense the machine starts learning, and that's where the word learning comes from in the machine learning attribute. In general, machine learning breaks into 2 categories, what we call supervised learning and unsupervised learning. Supervised learning is when you have outputs and inputs and you try to understand the relationship between the outputs and the inputs. If you think of that in econometric terms, you have y variables and you have x variables, and you're trying to find the relationship of y with x. You may be interested in a causal or predictive relationship. You may be interested in just a simple relationship without a correlation relationship as well. That would be supervised learning. Unsupervised learning is where there is no real output variable. You're trying to learn from the data itself. This is a much harder area to work in, but some things are very simple. Like clustering, for example, just takes a bunch of x variables about people and tries to put them into groups as well. But there are many other areas of supervised learning, unsupervised learning, that have become very hard, and those are more in the machine learning bucket. System-wide risk means we can't do what econometricians normally love to do, which is sample. If we just sample a part of the system, we may not actually understand entire system dynamics. And so when you're trying to understand systemic risk across a system, it becomes automatically a big data problem, falls in sort of this machine learning bucket. Now, when you try to understand risk across the system, what we're really talking about is how do different entities in the financial system or the economic system coalesce together or aggregate up together to give system-wide risks. That is, can we bring down the entire organism? So in some sense, if you think of the human body, it's a system with different organs. And we're really looking at the interaction between these organs and how they can cause the entire human body to fail. So for example, if you just have a problem with the liver, it has spillover effects on the other organs eventually, and eventually causing death. So that's sort of the thing that we try to worry about. So the first feature is that it is a big data problem because we have to have all the data in the system to be able to answer this question properly. And secondly, it's a data science problem because we want to exploit the health levels of all the institutions in the system, and we want to understand the interrelationships using networks. And to put all that together basically drops it squarely in the bucket of machine learning and data science. Midas is a project I did with IBM Labs in Almaden on the West Coast. And what they did was they pulled in every public sector public filing on the SEC and FDIC servers, so the 10Ks, 10Qs, all the regulatory filings. We text mined all these filings to pull out basic data. This is the same way in which Google actually mines the data that they collect from us when we use their browser or their services, like Gmail, for example. Google reads everything and starts tagging you under different tags. We would read every filing and sort of tagging it into different buckets, by loan, by security, by event, and so on. So we collected an enormous amount of data about these different entities through their filings, and then we looked for the relationships between the entities through the filings. So a simple case of this would be, every time a bank or a group of banks makes a loan to another bank, they have to file the loan document at the SEC. That's electronic upload of a PERD file or a PDF file, and we pull it down. This is a 100-page document. We text mine it, we pull out who lent to whom, and we can construct the interbank network of loans. And then we can look at that interbank network of loans and ask which is the most critical bank in the system. And if that bank fails or another bank that's also critical fails, how quickly will it bring down the system? We can construct mathematical metrics of what are the different qualities of this network, and when is the network in a fragile state versus not in a fragile state. If we shock the network, how does the ripple effect expose itself and cause aggregate failure? So that's what Midas basically does. It's a forensic system for pulling data from filings to understand at an aggregate level the interrelationships of all these entities. Now, in the early days, we could give a bunch of inputs, we had a bunch of outputs, and we tried to find the best weights of these neurons to actually, inside these neuron logit functions, to actually come up with a very nonlinear statistical model that says, given these inputs, that's your output, or that's what you do. And then because of back propagation in the neural net, we would learn. Now that was the original field of AI. Either it was sort of in the text area or in sort of relating outputs and inputs. And it never really worked very well because we didn't have computational power. And so the models never did better than a simple logit or a simple classification algorithm. What we've now discovered is, because computers have gotten so much better, if we build a neural network with 30 or 40 layers and throw all this self-driving car data at it, or translation data at it, or big macroeconomic data at it, we can actually produce very high accurate prediction models, simply because now we can compute these massive layers of neural networks. And so the only thing changed was computation power, but a technique that wasn't working really well on small networks is suddenly working remarkably well on large networks, which probably get closer to looking like the brain and being more AI. That's what we call deep learning. So today's concept of AI is now deep learning. Natural language processing doesn't work very well. Statistical language processing works really well. So we forget about the words as having nouns and subject and object and language characteristics. We just think of them as frequency counts. How many times does this word occur with that word? How many times does this word occur in most sentences? How many times does this letter get used? It's all statistical. So now all the tools just use deep learning to learn some relationships among words and text. It doesn't matter what language you're in, so they're more general purpose as well. That's also new AI. Now, it's not just that. Deep learning allows you to fit a model, but deep learning allows the model to learn a new model and to improve the existing model and morph into a better model. The other domains people worry about AI is privacy. They say, okay, these things are now going to snoop on everybody. They're going to figure out who's bad, who's good. That's already happening. There's nothing we can do about it. Our use of social media and bank statements and credit cards and all this stuff is throwing up a lot of information about it. If you're interested, you should go and look at a site called aboutthedata.com. That's a company called Axiom in Palo Alto that profiles everybody. Almost everybody in the world is in it. You can go in and put your name into aboutthedata.com and see what your profile is. There are two types of things that projects that were interesting in India. One is the systemic risk project, which we didn't use a lot of text mining. Though in the Midas project, we actually did a lot of text mining to construct the loan networks for banks, because that was one of the ways to do it. So we can text mine a lot of discussion about the banks in the news flow and figure out which banks are more related to other banks, for example. Another area of text mining that's become very hot is called topic analysis. And in topic analysis, what we do is we pull out all the news streams. So in India, for example, we could pull 5,000 different news sources every day, articles from them, and then we text mine each article to figure out across these articles what are the most important topics, and within each topic, how much of the news flow for the day is in a given topic. So for example, you could look at the news flow for today, and the algorithm would tell you that 60% of the news flow today was on inflation, 20% was on growth, 20% was on foreign currency. And so the central bank governor, for example, knows that today this was what was top of mind for people in the news. And then the next day, suddenly the component for inflation drops to only 20%, but the component for growth jumps up. He says, okay, something's changed, and I need to go look at what might have changed as well. So that's one way of monitoring the economy, where you pull all this out. Another way to use text mining is to actually look at the sentiment of the news and categorize it as whether it is positive, negative, or neutral within each topic as well. So if I identify oil as a topic, currency as a topic, growth as a topic, inflation as a topic, I then take all the news articles that fell into that topic and decide how many of them are sentiment positive, how many are sentiment negative. I can also see within each flow where that's happening. And some of the software that built in India actually shows the map of India with where the news is coming from, and with pie charts on every location showing the size of the news as well as how much of it was positive, negative. So we can even look at which parts of the country are currently demonstrating negative sentiment, which parts of the country are demonstrating positive sentiment. So text mining, I think, has a huge propensity to actually give us a lot of value. We can also look at text mining discussion because it might actually have an early warning signal in there. Now, one of the things, for example, we can do with companies is we look at their filings, their quarterly filings. They have to write a whole bunch of text to describe the fortunes of the company. And we've learned some very simple things by looking at that. One is that the number of risk words in the filing, we have lists now, lexicons of risk words. Number of risk words is a good predictor of a poor quarter performance. As that increases, next quarter tends to be worse. So we can sort companies by the number of risk words, and they sort next quarter's performance quite well. The other way you could do it is to look at how readable the document is. So readability is another aspect of text mining. We can look at a document that describes the fortunes of the company, and if you find it's not very readable, usually that's a signal that the company is not doing very well. Because when there's bad news, people tend to write it in a more complicated and confusing way. So there's a simple algorithm that decides this body of text is at 12th grade level, college level, and so on. So we read and we figure that out. The other thing we've learned is that when a company has bad news, their filing document is much bigger than when it's smaller. Because what they do is, it's like a kid who goes to an exam and he doesn't know the answer, so he keeps writing and he's trying to hide the fact that he doesn't know the answer in a lot of text. So bad news generally gets buried inside a lot of extra text. So that was another thing we discovered. So we then realized that we could just count the characters and find out whether a company was going to do badly or worse. So just to summarize, you can do the topic part of it, you can do the mood scoring of it, you can also summarize text. And text summaries are very effective because they actually allow you to collapse 5,000 news sources into a quick summary. And that makes your ability to actually capture trends earlier better, because now you're getting summaries which you can actually access rather than try and parse the tea leaves of too many different documents that are coming into you. The big data revolution is here. How can the IMF exploit the big data revolution? What do we need to do to make it an effective exercise? And what might be some of the relevant areas in which we can go first and try and get some leverage? So the first thing is, yes, I think there is no doubt that if an institution, especially one of this scale, doesn't get onto the big data bandwagon, you will miss a lot of the competitive advantages that are available to you. The second thing is, I believe that getting an advantage in big data is not waiting for you to have the perfect application on day one. I think building infrastructure around big data is worth it, even if we don't actually go into exploiting it right away. So I think just gathering data is valuable. Some economists, like Bob Shiller, for example, just gathers data, even though he may not have a research question in mind. And it turns out to be a very useful thing, because if you've collected the data, then it tends to lend itself to further analysis. And then when you get the question, you already have the data, your lead time in actually doing the analysis gets shortened. So I think getting the infrastructure ready for big data and populating your data sort of warehouse with these things is very important. The first step, of course, is to take a lot of the data that you already have collected over the years and sort of get it into formats that are accessible to all the research staff and the line staff in the IMF. The second thing is to start what we call data enhancement, which is collecting a lot of data that you currently don't collect because there may be no direct need for it, but you need to collect it. And this is data like news feeds from all over the world, because you're in every country possible. You have to collect news feeds from all over the world and so warehouse it in some way. Okay, so in some sense, what you're doing is just collecting a bunch of documents and indexing them. And the way this is done in text mining sort of jargon is you construct a term document matrix. It's exactly what Google does. It is constantly collecting and farming web pages and putting them into an index. And that's very easy to do. We have all the tools for it. So the infrastructure of housing it can also be handled because this cloud services that are very efficient and very low cost. Amazon Web Services, AWS is one of them, which a lot of people use. Anytime you need to scale something up, you can buy more. They also provide the CPU, so actually don't have to buy all the hardware for it. So it's kind of very simple and easy to use. Now, what are the different applications that the IMF might actually exploit in this area? One of them is early warning signals about the different regions and countries in which you operate. Just looking at economic time series is often too late. For example, if you look at the stock index of a country, usually the volatility goes up after the problem's already begun some time back. So you need to sort of get under the hood and look at the mechanics. And so the Midas project was a good example. We actually collected the loan filings, text mined them, figured out who was lending to whom, and constructed the network of loans. That gave us the connections between the banks much before any of those loans got bad. So we could look at that network and say, that networks look really concentrated in a few banks. Even though there's no trouble right now, we know that's a problem. And that's very different than saying, oh, suddenly the correlations have tightened, and now it's too late because the correlations have tightened when the problem's already arrived, and that doesn't really help very much. Okay, so we can do that. A lot of the text mining to do topic analysis is something that's very useful because you can then construct a whole bunch of real-time reports in real time that will actually allow you to notice that certain topics have suddenly changed in certain regions of the world and then act on those earlier, okay, than later. And so these are just some of the things that you can do right away. Another area which I found very interesting is to exploit email traffic. You already have all the emails between all the employees at the IMF, which are done for so many different work products that you have to produce because you've got people in different regions, you've got missions in different places, and people are all over the place, and they're communicating people back home in the head office and in other places as well. That email traffic is, in my opinion, an incredibly good early warning indicator. Just looking at the network of emails and suddenly seeing it change, or the actual content of the emails in terms of how many risk words are flowing through your network. Because unconsciously, many of the IMF staff will be detecting risk and reflecting it in their writing of emails and communication, but there is no formal report that's been sent. And a text mining algorithm that runs on the emails will be able to detect the quantity of risk words is suddenly going up and realize, okay, that's a region where probably problems are happening, and you can go and nail it down. Constructing all these networks, and in fact, there's a lot of good research papers at IMF that can be implemented now once you have this data. So that would be another area to actually work in. And deep learning will find relationships in the data that you never expected to find. I think given the amount of data you have access to and the different regions of the world that you have to operate in, just allowing a deep learning algorithm to actually run on all this data would produce, I think, completely remarkable results. It might completely change the way that policy is generated, because you might find that, oh, here's something that this country suddenly got better because all those variables changed. And those were not the variables that you sat down and wrote an economic model around. They could be completely unrelated variables. You never thought of putting an economic model together with all of those, but the algorithm will find it. And that's sort of the advantage of having this big amount of data.